Hello, this is Team 3 presenting our final project POGO-LOCO, short for Pogostick Locomotion. We first outline our problem and our general approach. Our objective is to control a pogo stick to track a desired velocity. A pogo stick is characterized by its floating base and a single spring-loaded contact. Locomotion of the pogo stick consists of orienting the system while in the air and injecting proper ground reaction forces while in contact with the ground. There are four main challenges in Pogostick locomotion. To control a pogo stick, we have to control a highly nonlinear system with underactuated actions to maintain a dynamic and rhythmic motion with sparse opportunity for correction. To simulate these challenges, we created a simple URDF file with 4 degrees of freedom. The bottom prismatic joint is a passive joint that simulates the spring, while the 3 active joints simulate human motions of tilting and translating the body. Additionally, we employed a physics engine, RISIM, and its accompanying RL framework, RISIM-GYM Torch, to accurately simulate and generate samples in parallel for our learning-based controller. Now we formally define our problem of POGO-LOCO in the realm of reinforcement learning. Below is the typical RL setup. Our agent is a learning-based controller with an actor and a critic. Our environment is the simulation stated before. Now we specify our observations, actions, and rewards. For actions, the policy decisions must be feasible in the real world. It is common practice for this to be the force applied to each actuator, so that is what we chose. Observations must be carefully defined with equivalence and real-world settings in mind, restricting hard-to-measure quantities like base velocity. For defining rewards, these constraints can be relaxed to focus on shaping the desired behavior. We use different observations for our actor and critic. As stated before, a realistic actor must only use unprivileged information, which is data that can be obtained from sensor measurements. However, since the critic is only used in training and never deployed in the real world, privileged information is used to enhance its performance. This difference can be interpreted as the actor given partial observability, while the critic is granted full observability. The definition of reward quantifies our objective. There are 3 objective reward terms that directly encode the objective: punishing falling down and encourage following velocity commands. Additionally, style reward terms help stable training and guide desired behaviors. Further details are shown in the appendix. Now we explain our methods. In line with our observations, we use different architectures for our actor and critic. To address partial observability through sequential dependence, the actor network contains GRUs or gated recurrent units. However, since the critic is provided full observability with privileged information, the critic network is a simple multilayer perceptron. We chose PPO for our training algorithm since it provides stable convergence while guaranteeing trust regions. PPO is especially strong for parallelized simulation setups where sample inefficiency is not a problem. Refer to Lecture 8 for further details. Now we showcase our results. We trained our policy with 4.4 billion samples spanning up to 11 hours. It shows intuitive rhythmic hopping motions while tracking both linear and angular velocity commands. The latter is especially impressive since the system does not have any degree of freedom to rotate in place. Additionally, our policy exhibited robustness against various environments and disturbances that were not encountered in training. Finally, we discussed the effectiveness of our methods with a series of ablations. We compare our original policy with training results from different settings. When the critic network is trained without privileged information, the resulting policy cannot achieve stability at all. Next, when the actor network is trained without recurrent components, the resulting policy struggles with following the command velocity. These comparisons show that our methods with privileged information and recurrent architecture was crucial in obtaining our result. Here are our references. Thanks for watching. For additional information and appendix, please check the description below.